All right, welcome back, everybody. So I'll start by just kind of briefly recapping some of what we went over on Monday, and then I'll jump into the new stuff. So let's imagine we're in a canonical ensemble. And so as per usual, we write our partition function. Q is a function of nbt. And then that's sum over all states j of the exponential of beta times the energy of that state j. Now we can make some assumptions that allow us to deal with this system. So if we don't make any assumptions, it's not really tractable to solve this n-body problem and figure out what these energies are. So we can say if our subsystems can be treated independently, then we can write our overall Hamiltonian for the system as a sum over our degrees of freedom that are independent. So a separate Hamiltonian for each of these independent degrees of freedom. And so if our Hamiltonians are separable in this way, then that means by definition our energies are also separable in this way. So similarly, we can then rewrite our overall system partition function as the product over these degrees of freedom. Big Q, now we have this single particle or molecular partition function, where in the previous class, I divided up these molecular partition functions, each one pertain to a single particle, whereas for most of this class, we'll actually show that each of these individual particle partition functions can actually also apply within a single particle to separate independent degrees of freedom. But more on that. And now we have this molecular partition function, which it has the same form as the system partition function, but now just pertains to a single particle or degree of freedom. So the subscript I corresponds with a particle or degree of freedom, and then our subscript j would then be over states for that particle. So now kind of stepping through and making another assumption, change up my colors here. So if the particles are identical, and what we mean by identical here through is distinguishable, so I can look into the box and say this is particle A, this is particle B. Then I can write the overall partition function as the single particle partition function just raised to the nth power, where I have n particles or n degrees of freedom. Now, more commonly, the case is particles are indistinguishable. So that means that because I can't distinguish between two particles, if I have particle 1 in state 1 and particle 2 in state 2, this looks the same to me as the inverse, where particle 1 is in state 2 and particle 2 is in state 1. So I need to account for overcounting in some way. The one way to do that is just to divide by all of the web if each particle can have its own state. So if the number of states is much larger than the number of particles in the system. So generally, if we think about how the number of states grows or decreases, this is generally good at sufficiently high temperature or sufficiently low density. So if we have high temperature, we're exploring a lot of states. If we have low density, then there aren't that many particles. Now let's say if we can't apply Boltzmann. So this would be at low temperature or high density. Then we have to think about the quantum regime. Whereas when Boltzmann's approximation is applicable, we call that classical mechanics. So in the quantum regime, we think in terms of occupation numbers. So how many particles are occupying a given state? And in the context of occupation numbers, that creates some constraints on our system. So we have a couple constraints. If we sum over all the states in the system, the occupation numbers of those states, then that must add up to the total number of particles. And then a second constraint would be that if we perform the same sum, but now multiplying by the energy of that state, that's equal to total energy. Now there are two kinds of, so the main difference here between these two types of particles is the maximum number of occupations. So what's the maximum number of particles that can sit in any one state? And so for bosons, the max occupation is infinity. So you can keep adding particles to states. And for the other types of particles, fermions, no two particles can occupy exactly the same state. So the maximum occupation of any state is just one. So fittingly, we call the statistics or the distribution statistics for bosons Bose-Einstein statistics, or BE. And then for fermions, Fermi-Dirac statistics, or FD. In terms of maximum number of particles that occupy any one state, the corresponding partition functions and probability distributions look really similar between these two types of particles. For fermions or bosons with this general form. So it's the product over all states I of 1 plus or minus exponential of minus beta, the energy of that state minus the chemical potential, and then raised to the power of plus or minus 1. And so in this general expression, for fermions, we use the plus, and for bosons, we use the minus. And now performing a similar workup as we've done before, trying to go from statistical mechanical space to thermodynamic space. So that's going from partition functions to energies or some average properties. Average occupation number of a state for fermions, for bosons, has this general form of 1 over e to the beta times epsilon minus. And just as in the partition function for fermions, we use plus, and bosons, we use minus. All right, so if we look at kind of what are some of the limiting cases, so if the energy of the level we're interested in is much larger than the chemical potential, then thinking about the average occupation of that state with this large energy. For bosons, the average occupation of that state goes to just the Boltzmann factor. So I'd be plugging in a very large value for epsilon. We say that mu is effectively negligible, and then we get the Boltzmann factor. This is actually also the case for fermions. And so at sufficiently high energies, both of these distributions just behave like a Boltzmann distribution. Now, in kind of the opposite limiting case, if the energy is equal to the chemical potential, then for bosons, we get what's called a Bose-Einstein condensate. And the occupation of that energy level just goes to infinity. So none of the bosons are exploring higher energy states. And for fermions, we get kind of the same thing, because the occupation is 1/2. So I'll draw a quick picture that should make this a little more clear. So if I plot what is the average occupation number of a state as a function of this term that appears in the exponential, so this is beta times epsilon, or the energy of state I minus the chemical potential. And then let's see if I can draw this morning. Put a 0 there and a 1 here. So for fermions, as we go to very low energies, the occupation becomes 1. Then for bosons, the occupation is very high at low energies, kind of asymptoting at 0. And then the Boltzmann distribution looks very similar to bosons, except it allows occupations at these energies minus chemical potentials less than 0. So again, these are bosons, classical particles in orange, and then fermions in blue. All right, have any questions? This is kind of the end of the recap from Monday's lecture, and then I'll jump into some new stuff. Yeah, so basically in the definition of chemical potential for bosons, it can't be less than the energy. So we get an asymptote that goes to here. So you can kind of see in this expression that if mu, or at 0, let's say, so epsilon minus mu equals 0, then we would have for boson 1 over 1 minus 1 equals 1 over 0. So just the statistics, or the average occupation goes to infinity as epsilon minus mu approaches 0. And that's really just in the definition of chemical potential for bosonic particles.
Okay, thank you.
Yeah. All right, so where are we headed today? So today, instead of thinking in terms of how do we separate an overall system partition function into a bunch of molecular partition functions, each for different particles, now we'll be thinking about how do we take a single particle partition function and even break that down into simpler problems that we can solve. So the simplest problem in this space is a monoatomic ideal gas. So we call this gas ideal, meaning the particles are non-interacting with one another. And for the purposes of our workup, what this means is we can say that there are independent subsystems. So very similar to what I showed earlier, that allows us to say that the overall system partition function is a product over these molecular partition functions, one for each molecule or particle. So as I was kind of alluding to, we can further subdivide this single particle partition function, and we can say that this single particle molecular partition function is actually the product of a bunch of partition functions, each for a different independent degree of freedom for that particle. So now J here is degrees of freedom for particle I. And importantly, these should be independent so that we can take their product and get back the single particle partition function. All right, so let's consider we have our monoatomic ideal gas of particles that are in a 3D box. Kind of a classic problem in quantum mechanics. So we can define what are the energy levels in this system for each quantum number. So nx here is the quantum number or state in the direction x, y, and z, so each direction of our box. So we know that from solving Schrodinger's equation, we can get that these energy levels look like this, where there's a squared dependence on each axis in our box. Where again, these n's are just quantum numbers. So nx equals 1, 2, 3, and so forth. All right, so then we just write our partition function now that we know what the form of the energy looks like. So the general way that looks, we sum from all of our states 1 to infinity of beta times these energy levels. So I've written this kind of condensing nx, ny, and nz into one variable, but we can also expand those. So we can kind of write a triple sum, summing over each of these positional degrees of freedom. And now expanding what we just wrote out for the energy. So that's beta times h squared over 8 times the mass times the length of the box squared. And then a squared term for each position. And then each of these sums goes to infinity. So because we have a box and there's nothing distinguishing any of the 3 dimensions from one another, we can just write that as a single sum. And then cubed. So an assumption we'll often take when we have many particles in a box or many potential energy levels that are densely packed. We'll say that assume spacing of these energy levels is small. And so that suggests that we have a more or less continuous distribution of energies, and we can rewrite this sum as an integral. So now Q equals the integral of this same expression minus beta, exponential of minus beta times the energy. And then all of that cubed. So this looks like kind of a messy integral, but there are actually a number of different ways that we can handle this. The way I'll show in this class is by using the definition for a Gaussian integral. So for a Gaussian integral, we know if you integrate from minus infinity to infinity of something that has this form, this definite integral just equals pi over a, or the square root of pi over a. So we note that there is kind of a change in the lower limit of this integral. So we know the definition of the Gaussian integral from negative infinity to infinity, but we can't have negative states. So we're only interested in the integral from 0 to infinity. But we know that this function e to the minus x squared is even. And so even function, the integral from minus infinity to infinity just equals 2 times the integral from 0 to infinity. So if we divide this by 2, we know the integral over the domain we're interested in just equals the square root of pi over 4 times a, where a in our case is this constant coefficient that pops out. So if we plug that into our expression for Q and use the definition of the Gaussian integral, we get that the translational partition function for monoatomic ideal gas is 2 pi kBt times the mass divided by Planck's constant squared, all of that to the 3/2 times the volume, where I've swapped out the A meaning the length of the box. It becomes cubed, and so we can take that out and just take the volume. So we arrived at this partition function for translations initially by summing over states. So remember, right at the beginning, we got here by saying that Q equals the sum over all states of the exponential minus beta times the energy. But we can also get here if we sum over energy levels instead of states. And this brings in the density of states, or the degeneracy. So we can write Q, again, assuming densely packed energy levels, is the integral from 0 to infinity of the degeneracy times the exponential of minus beta of the energy, and then we're integrating over these energy levels. So what is this omega? This omega we call the degeneracy, or the number of states between some energy and an increment in that energy. So from the same kind of classical quantum mechanical problem of the particles in a box, we know the density of states can be written like this. So that's the degeneracy times this increment in the energy equals pi over 4 times this similar term, 8ma squared over h squared to the 3/2, and it goes with the square root of the energy and then times the increment in the energy. So now moving all of these constants out and rewriting our integral for Q. So what appears in the integral from 0 to infinity, so we're integrating over our energy levels, but we have the energies to the 1/2 power, again, times our exponential in the energy. So if we remember our differential equations classes, we can write a Laplace transform, or the solution to a Laplace transform takes the form of some function of t times e to the exponential of t dt. And so in this case, we have some function of the energy times the exponential to the energy. And if we look up what is the Laplace transform of this expression, we get the same Q as before. Now, what's interesting about the fact that we got here from a Laplace transform is that it implies that some bidirectionality here in transform. All right, so this is our translational partition function for a monoatomic ideal gas. So let's look at the form a little bit. So we see that here we have volume, so that takes the units of length cubed. And then we have some stuff that we're taking to the 3/2 power. So that means this has units of 1 over length squared. And so that means there's some kind of parameter with the unit's length embedded in this somewhere. So we define that quantity as the de Broglie wavelength. I'll probably say de Broglie at some point by the end of this lecture, but I don't want to insult any French students we might have here. So the de Broglie wavelength has the symbol uppercase lambda, and that equals h squared over 2 pi times the mass times kT, all raised to the 1/2 power. And so this has units of length. Recognizing again that our partition function should be unitless, so these units have to cancel out. So now let's go back to our overall partition function, which then allows us to start getting some thermodynamics from this guy. So if translations are our only active degree of freedom, then our overall partition function is just the product of the translational partition functions for each of our particles, I. And if we assume we're in a Boltzmann regime, then we're assuming that the number of states much greater than the number of particles. And we can write our big Q equals small q, which is just the translational partition function raised to the nth power divided by n factorial. So if we sub in what we have for the translational partition function, we have 3 terms, 1 over n factorial times the volume raised to the nth power, and the de Broglie wavelength raised to the minus 3n power. So we're in a canonical partition function space. So our thermodynamic potential of interest is the Helmholtz. We know that the Helmholtz free energy is minus kBT times the natural log of our system partition function. So now if we plug it in and kind of then start to do some manipulations with the logs, so this would be minus KT times minus the natural log of n factorial plus n times the natural log of volume minus 3n times the natural log of the de Broglie wavelength. So here I'm just kind of taking these powers and popping them down to the multiplier of the log. All right, we can take an n out of this expression. So we have minus nkt times minus log n plus 1 plus the log of v minus 3 times the log of the de Broglie wavelength. And so here I'm invoking Stirling's approximation for the log of n factorial, which gives me this log n plus 1 once I remove this n from the entire expression. So this is our expression for the Helmholtz free energy. And then if I want to get some meaningful thermodynamic quantities like the pressure, I can say the pressure is the minus of the partial derivative of the Helmholtz free energy with respect to volume. So I take the partial derivative of what I just wrote a second ago. And so the only term that has any volume dependence is this log v. And so now the pressure is the minus partial derivative of minus nkt log v. And I hope that this is starting to look familiar. And so if you remember that we have a monoatomic ideal gas, we take this partial derivative and we get that the pressure is nkt over the volume, or the ideal gas law, which is PV equals nkt. I should have asked Zhengyan for a drum roll there, maybe. Okay, does that all make sense? Do you see how we go from statistical mechanics space, we get our partition function, we perform some logs and partial derivatives, and that gets us to the thermodynamic space and recovers our ideal gas expression. All right, so we can also think about other properties. So what about the chemical potential? So we can think about the chemical potential as kind of the energy penalty to add or remove particles from the system. So mu is the partial derivative of our Helmholtz free energy with respect to particle number with T and P constant. So then just plugging in what we came up with before for the Helmholtz free energy. This is minus nkt minus log n plus 1 plus the log of v. I'm going to run out of space. Minus 3 times the log of the de Broglie wavelength. So if I take this partial derivative and do some log manipulations, I get minus log n minus 1 plus 1 plus log v minus 3 log the wavelength. So these guys cancel each other out. Volume I can rewrite using the ideal gas law. Equals nkt over p. Do some more log manipulations and get that mu equals kt log n minus KT log NKT plus KT log P plus 3 KT log de Broglie wavelength. So these KT log n's will cancel with each other. And eventually I get mu equals KT log P plus 3 KT log of the de Broglie wavelength minus KT log KT. So what does this tell us about the chemical potential of an ideal gas? It says, one, there's a log dependence on the pressure. And then there's this term that if we remember what goes into the de Broglie wavelength, it's really just the mass. Let's see if I can bring that back up. So the only system-specific quantity here is the mass. So now there's this other term that's more or less constant once we define the system, or constant, but a function of temperature. So we call this the reference chemical potential, which is a function of temperature. And it just contains terms mass, T, and then some constants. So even though this is a pretty idealized system, we actually use this log dependence of the chemical potential on pressure when designing chemical reactions. So one system in particular that I worked on in my PhD, let's see, it's called chemical looping, or thermochemical water splitting. So in this kind of setup, we have a cycle of two reactions. So one reaction, we start with a metal oxide that has X moles of oxygen per mole of metal. We add a ton of heat, and that drives off some of the oxygen from this material. So we call it a reduced metal oxide, and liberates some oxygen gas. And then the second step of the cycle, we're trying to make hydrogen from water, and we want to reform this metal oxide. So we take our reduced metal oxide, expose it to steam. So that reforms our oxidized metal oxide, this MOX, and then liberates our valuable product, hydrogen. This is a very high temperature process. So we usually do this step at about 1500 C, and this step at maybe about 1000 C. So you can imagine these two reactions, we want both of them to be spontaneous at the conditions that they operate. And so that's really tricky because we're kind of forming the oxidized metal oxide in one step and decomposing the oxidized metal oxide in the other step. So one thing that we can do is operate these systems at different pressures. So if we imagine, just focus on this step one. If we compare two cases, so if we have case one, we just use atmospheric pressure. So the pressure of oxygen, let's say, equals 1 atmosphere, although if you factor in the concentration of oxygen, maybe it's, if we're running in air and not pure oxygen, it's about 0.2 atmospheres. Or we could consider case two, where we're removing oxygen from the system. So some systems can get oxygen down to, say, 1 parts per million. So 10 to the minus 6 atmospheres. We might do this in practice by just flowing a lot of nitrogen into the system while we run this reaction, or we could be pulling a vacuum to remove all of the gas particles. And so how does that help us in terms of these reactions? Well, we can say that the overall thermodynamic driving force for this system, delta phi of this reaction one, is going to be the Gibbs energy of that reaction minus the chemical potential of oxygen times the number of oxygen molecules that we're adding or removing from the system. And so by changing the partial pressure of oxygen, we know that we just created a or we just showed that there's a log dependence on how the chemical potential of oxygen is related to the pressure. And so we can say that mu O equals mu O ref plus RT times the log of the pressure of oxygen divided by the pressure of the reference state. And so by switching to this case 2, how much driving force are we adding? So if we plug it in, RT times the log of, say, 10 to the minus 6, that's about 200 kilojoules per mole. So we can take what's nominally a very uphill or endothermic or endergonic process, this reaction 1 driving oxygen out of a metal oxide. And then just by modulating the pressure or concentration of oxygen in our system, because there's this log dependence on the chemical potential, then we can actually create this driving force kind of out of nowhere, which is pretty cool. All right, so that's all for that quick aside. So back to our ideal gas, our monoatomic ideal gas. I guess before I move on, does anyone have any questions on how we're getting thermodynamic properties from the statistical mechanical world? All right, sounds good. Everybody's got it. So just remind you what our overall partition function looks like. We have this term 1 over n factorial that comes from the Boltzmann's approximation times the volume to the nth power and the de Broglie wavelength to the minus 3n power. So similar to how we got the Helmholtz energy, we can also get the internal energy. So the energy for this system is just kT squared d log q dt. So if I plug some stuff in, kT squared dt times the log of all this stuff that's in Q. So if we look at these terms, we're taking a partial derivative with respect to t. So neither of these guys have t dependence. And because these are in a log, when we take the partial derivative, these will just go away. So we really just want to take the log of the de Broglie wavelength. So we can say that the energy eventually comes out kT squared ddt so the energy becomes 3/2 nkt. So we know the specific heat is then the partial derivative of the energy with respect to temperature. And so that just equals 3/2 nk. So this is a pretty famous result in the statistical mechanical world. And it's called, or it can be derived, that this is the Equipartition Theorem, which states that each degree of freedom in a system contributes 1/2 kT to the energy. And so kind of more specifically, it's not any degree of freedom, but any degree of freedom that's quadratic in the Hamiltonian. So for our system, a monoatomic ideal gas, we say the energy is 3/2 n, or sorry, 3n times 1/2 kT. So that means that we have 3n degrees of freedom. And the reason we have 3 is because we have, or 3n, we have n particles, each of which can undergo translations. And then each of those translations can occur in the x direction, y direction, or the z direction. And so that's where the 3 comes from. So we have 3-dimensional translations. And so 3n degrees of freedom in the system. So a while back, we got to this by assuming Boltzmann's approximation was valid. So it's generally good to remind ourselves what we mean by that, or when is this generally valid. So this allowed us to say that we can correct for overcounting our indistinguishable particles by dividing by n factorial. And in our case, this is generally valid as long as the volume of our system is much larger than the de Broglie wavelength cubed. Which is kind of a way for us to say that we're at sufficiently high temperature or low density that Boltzmann's approximation is valid. All right, so this is the end of monoatomic ideal gases. I'll pause for a second before we move to diatomic gases to see if anybody has any questions.
This might be a silly question, but for all the K's, they're the Boltzmann constants.
Yeah, exactly. So sorry, yeah, I dropped the B, but these are all Boltzmann's constant K.
And how does that relate to the ideal gas constant for the PV equals?
Good question. So yeah, I'll scroll back to this guy. So here I wrote RT. So this is just NK. So Avogadro's number times K is the gas constant.
Oh, okay. Thank you.
Yeah, sure. All right, so on we go. So from monoatomic gases to diatomic gases. So we're going to try to apply a similar workup where we think about the degrees of freedom in our system. But because we now have two particles connected together by a bond, we have slightly different degrees of freedom than in the monoatomic case. So we still have translations. And these are actually the same. Which means that our translational partition function is just going to be the same form that we showed before. But now, because we have a chemical bond in each of our particles, in addition to translations, we also have vibrations. And to get after these, we're going to model our particle or our diatomic molecule as a quantum harmonic oscillator. So a harmonic oscillator looks something like this. If we have our diatomic molecule, these two red dots, in reality connected by a bond, but we'll kind of imagine that they're connected by this little spring. We can draw what is the potential energy for displacements along this axis. So along the distance of the bond or along the stretching axis. And we'll have some potential energy that looks kind of like this. So where it's lowest energy when it's at its equilibrium position, and then there's an energy penalty for compressing or stretching the spring or bond. And we know it's a quantum system, so these energy levels are quantized or discrete. And we can write an expression for these energy levels, epsilon sub n equals n plus 1/2 times Planck's constant times the frequency of these vibrations. So now this is our quantum number or state number. Planck's constant is h. This is the frequency, nu. And then this 1/2 comes from the 0-point vibrational energy in a harmonic oscillator. So what dictates the vibrational frequencies of a system? We can write nu equals a function 1/2 pi times, sorry, now I'm using a different k. So this k in the vibrational partition function workup will be the spring constant. And I'll try to use k sub b for Boltzmann's constant when it shows up, but please just ask if you're confused on which k is which. So this is the spring constant, which kind of represents the bond stiffness in our molecule. And then mr is the reduced mass, where if we just have kind of m1 connected to m2, the reduced mass equals m1 times m2 divided by m1 plus m2. All right, so now we know how our energy levels depend on the frequency, and we know how our frequency depends on the internal parameters of the system. So let's try to come up with our partition function. So just like always, the single particle partition function is the exponential of minus beta times this single particle energy, epsilon sub n. So we know what that looks like. And we can remove this term that has to do with the 1/2 because it's just a constant. And we'll take this from 1, sorry, it should be an n. Maybe you can hear my neighbor's dog barking in the background. It's a lovely addition to my workday. Okay, and so now we have this sum that actually takes a form that we hopefully look familiar. So we saw previously that the sum, the infinite sum of x to the n from 0 to infinity, sorry, these should be zeros, but it doesn't really matter too much. So the infinite sum of x to n from 0 to infinity is just 1/1 minus x. And so we saw that workup previously for Bose-Einstein statistics. So then we can write the solution to our vibrational partition function. Oh. Is this constant e to the minus beta h nu over 2 divided by 1 minus e to the minus beta h nu. And this beta h nu is actually an interesting quantity that emerges here in the exponential. So beta h nu is h nu divided by kBt. So we know kBt is kind of like the thermal energy in the system. And h nu is like the vibrational energy. As kind of a general rule of thumb, beta h nu is usually much larger than 1, unless we're at really high temperature. So this has an implication that the energy levels for vibrational systems are kind of sparsely spaced because the frequencies are generally high relative to the temperature. But if we're in the case where beta h nu is much less than 1, then we have densely packed energies. And so we integrate. So we could rewrite our vibrational partition function like this. So here I'm just replacing the infinite sum I showed before as an integral. And if we solve this definite integral, we can say that if beta h nu is small, then this goes to 1. You know, this is 0. And so our vibrational partition function just reduces down to this quantity 1 over beta h nu, or kt over h nu. So just to be a little bit more convenient in terms of handling this relationship between vibrational energy and thermal energy, we define this quantity, the vibrational temperature. Theta sub v. So we say that kb times theta sub v equals h nu. So that just allows us to think about these vibrational frequencies on a temperature scale. So if theta v is equal to h nu over kb, then we know that theta v is proportional to these vibrational frequencies. And then if we recall our expression for the vibrational frequencies, this is proportional to now the spring constant k divided by the reduced mass m raised to the 1/2 power. So this tells us that we'll have high vibrational temperature when we have stiff bonds. So large K. Or very light atoms. So that would be decreasing mass. So the frequencies of our vibrations are then related to these two quantities. So just give you an idea of the scales here. So for hydrogen, which is a pretty stiff bond and extremely light atoms, the vibrational temperature is on the order of 6,000 Kelvin. Then the other end of the diatomic spectrum for iodine, we have a big heavy atom, not so strong of bonds. The vibrational temperature is about 300 Kelvin. So then I can rewrite my partition function in terms of this quantity. So remembering that that was e to the minus beta h nu over 2 minus 1 minus e to the minus beta h nu. In terms of vibrational temperature, that becomes e to the minus theta v over 2t and 1 minus theta v over t. All right, so getting back into the thermo world, that means we're going to be taking logs to try to get thermodynamic quantities. And the energy is going to be the number of particles or oscillators times kt squared times the partial derivative of the log of the vibrational partition function with respect to temperature. So skipping a bit of the math details, we get that our vibrational contribution to the energy is nk times our vibrational temperature over 2 plus the vibrational temperature over this exponential. And you can just take my word for it that if we're at low T, this term goes to 0. So how does the vibrational temperature affect the occupation of different energy levels? So if I plot, oh, that's squiggly. So if I plot my energy levels here, so kind of 0, 1, 2, 3, and so forth, and then the probability of occupying those energy levels. If we look at this expression for the vibrational energy, we see that it's related to the vibrational temperature. And so if we have very large vibrational temperature, these energies will be really spaced out. So we have high frequencies, so the spacing between energies gets very large. And the way that manifests here is that means we'll have a very high population of these low energy states. So it's very difficult for when you have a large vibrational temperature to actually explore these very high frequency modes or these large N values. Whereas if we have a small vibrational temperature, this is kind of smoothed out quite a bit more. So small vibrational temperature, the energies are more densely packed. And so it's easier for the system to explore these higher N values or these higher states of energy. All right, and of course, by now we know that the heat capacity is, or the vibrational contribution to the heat capacity is the vibrational contribution to the energy, the partial derivative of that with respect to T. So again, skipping a bit of the math, this comes out to nk times theta v over T squared. And then this exponential, which has theta over T. So as we go to high T, so as T increases and theta over T approaches 0, then this whole term goes to 1. And so that means that if we're at sufficiently high T, the heat capacity from vibrations just goes to N times K. Are there any questions on the vibrational workup before we jump into the last degree of freedom?
Like, what's a rough physical interpretation of the vibrational temperature?
The physical interpretation would kind of be what actual temperature is needed to activate a significant amount of high energy frequencies, if that makes sense. So if my real temperature exceeds my vibrational temperature, then that means I'm populating some of the non-n equals 0, n equals 1 type vibrational frequencies or energy levels. Does that make sense?
Yeah, thank you. And what's the y-axis on the graph right there?
That's roughly the probability of being in that state n.
Okay,
So
thanks.
the probability of a particle exploring these higher energy levels. All right, thanks. So back to our particles. I'll leave some of this up here. So we have translations. These are just the same as our monoatomic case. Talked about vibrations, which we model the system or the particles as harmonic oscillators. And then our last degree of freedom for diatomic particles is rotations. So rotational degrees of freedom are not the most relevant systems for material science, so we'll kind of cut to the chase. At high temperature, the rotational partition function is just the temperature divided by the rotational temperature. And the rotational temperature kind of has a similar meaning as the vibrational temperature, but now applied to activating these higher energy rotational states. So this comes out to be 8 pi squared times kb times the moment of inertia divided by Planck's constant squared times the temperature. And this I is the moment of inertia for our rotation. And then once again, this theta is just trying to put our degree of freedom of interest onto a scale we're familiar with. So onto a thermal scale. So instead of kind of trying to have to remember what is a large or a small moment of inertia or vibrational frequency, it just gives us kind of a shortcut to thinking about the magnitude of these things. So in general, theta r is pretty small. So for example, a large theta r would be for a hydrogen deuterium diatomic particle. And even then, theta r is only about 40 Kelvin. So just in terms of rough magnitudes, the vibrational temperature is much larger than the rotational temperature. And the way that manifests itself here is if we make a similar plot as before. So again, n being the states, the energy states, p of n being the likelihood that our particles are in these states. A typical vibrational curve would look like this. So we're really only occupying these low values of n. So because the vibrational temperature is large, it's difficult to explore these very high energy vibrational states. But for rotations, we get much larger occupation of these larger values of n. So this green would be rotations, and this pink would be vibrations. So the actual shapes of these curves is not super important, or at least the shape of the rotational curve, but it's just a way to kind of visualize what does this really mean when we talk about the temperatures related to each of these degrees of freedom. So again, the rotational partition function we approximate as T over theta R. So that's assuming high temperature, but that's usually a pretty good assumption because our rotational temperatures are so low. So then the rotational contribution to the energy, just as before, nkt squared times the log of this particular degree of freedom's partition function, or the partial derivative of that. And because this is just related to linear and temperature, this comes out to nkt. And our rotational contribution to the specific heat is just nk. So now summarizing how our diatomic gas, diatomic ideal gas, and the specific heat. So we showed that the translational contribution is 3/2 nk. The vibrational, just nk, and the rotational, nk. So just to kind of remind you where these magnitudes come from, it's related to the quadratic degrees of freedom in the Hamiltonian. So we get half of a kT in the energy, which means we get half of a nk in the total heat capacity. And so there are 3 degrees of freedom for translations. So that's why we get 3 times 1/2 nk. And that's related to doing translations in our 3D space. There are 2 degrees of freedom for vibrations. So one is related to the angular frequency of those vibrations, and then one related to the position coordinate, so where those atoms are relative to one another stretching. And then again, we have nk, so that's 2 degrees of freedom for rotations. And this involves the 2 ways that we can rotate a rigid rotor. So there's kind of one way you can rotate and then the other, but you can't rotate kind of along the axis of the bond. Otherwise, that's just a translation. So one thing that becomes apparent here is that it doesn't look like any of these contributions to the heat capacity actually depend on temperature. But we know from experiment that the heat capacity is actually a strong function of temperature. And so how does that actually happen? Does anyone have a guess of why, even though we're saying that there's no T directly in any of these contributions, why we know that the heat capacity is a function of temperature? Anybody want to take a stab?
Is the frequency of vibration dependent on temperature?
That's a good question. No, not exactly, but the frequencies we can access would be a function of temperature. So not the frequencies themselves. So that actually leads in. So it has to do with kind of the temperatures at which we're activating different degrees of freedom. So if I plot the temperature here, and then the heat capacity in units of 1 over nk. So I pretty much always have translations. So my low temperature heat capacity might be 3/2 nk. And then it takes some amount of temperature to activate rotations, and then some amount of temperature to activate vibrations. And so here I'm adding 1 nk, so that'd be 5/2, and then here I'm adding another nk, which would take me to 7/2. So these are not exactly the rotational and vibrational temperatures, but this first one is kind of proportional to the rotational temperature. And then this one would be proportional to the vibrational temperature. So we always have translations, but we need a sufficient temperature to activate the rotational degrees of freedom, and then a higher temperature typically to activate the vibrational degrees of freedom. So does this concept make sense? So this is kind of a physical interpretation of what these temperatures mean. It's roughly the temperature needed to activate certain degrees of freedom. All right, and then just a quick look ahead. So what about our best friends, the solids? So we know, perhaps you know if you've taken solid state physics, that the heat capacity goes to 3 NK. And that implies 6 degrees of freedom. And we're in solids, so we don't have translations. We don't have rotations. But we do have kind of a network of bonds in all 3 dimensions, which means we have 3D rotations, or vibrations, sorry. So 3 vibrational degrees of freedom equals 6 total degrees of freedom. And so all of our heat capacity comes from vibrations for solids. And this will be pretty much the entire topic of next lecture. So just a little snapshot. So that's all I have for today. Feel free to ask any questions if you have them, and then I'll stick around for a few minutes after if you have any more questions. Thanks.
Are you able to say anything about what the transitions shape between the in that plot of CV over NK versus T?
So this is definitely an idealization where it's like a step function. So it's much smoother than this. But yeah, I'll show some CV versus T curves for solids on Friday. But yeah, it's generally much smoother than this.